Hey class, Mr. Hofstad here, and I'll go through this first PowerPoint up to damping with you today. Most of this is a review from our first half of Unit 5 in Physics 20. So if you're feeling a little rusty on that, it might be a good idea to go back to that, look at some of the examples, try out some of the homework questions, because really not much is changing. At this part at least. We'll get into some new concepts like angular velocity and a couple new formulas, but for now this lesson is mostly a recap. So let's dive right in. Hopefully you had a chance to watch those two videos, or those three videos actually. Uniform circular motion, simple harmonic motion, and the other one that wasn't a crash course video. That was actually my favorite of the bunch. So we can kind of see a really close tie between uniform circular motion, right? This red dot going around the circle here, and the simple harmonic motion in one dimension of the object, right? If we were to just flip this circle 90 degrees, right, rotate it, look at it horizontally, this is how it would appear. Right? And the connections between them are all over the place. They're very present throughout this whole topic. So having a strong understanding of both uniform circular motion and simple harmonic motion, they're directly related to each other. And here's just another neat graphic, right? We're seeing the displacement of either a spring, right? An object on the end of a spring or a pendulum, whatever it is, and the velocity, which is maximum when displacement is 0, and the acceleration, which is always opposite, right, but proportional to our displacement x, right? So those are kind of the three main quantities we're interested in for simple harmonic motion. So let's get going. Yes, cows do tend to sit on cars. Alright, so displacement x is always measured from the equilibrium or that rest position, right? So this dotted line down the middle of this sinusoidal graph is our equilibrium position, and displacement, right, would be positive above, negative below. But it's always measured, right, that red arrow, from our equilibrium position. Amplitude is always the maximum displacement, so the distance from the equilibrium to a peak or to a trough will be the amplitude. There's an important quantity we have to keep in mind, right? So it'll always be how far away this object undergoing these oscillations is from equilibrium. Right, so amplitude is how far away it is. Period is how long it takes to do a complete oscillation. Right, so all the way down, all the way up, back to where we started. Right, so it doesn't necessarily matter where you're starting your motion. Right, this one is starting at equilibrium, then being brought down, coming all the way up and back to equilibrium. Right, we could just as easily start at a trough, right, from the bottom. That's going to be similar to our first lab we're going to do. And then it'll travel all the way up. And once it reaches that bottom position, right, where it's at its furthest point below the equilibrium, that's when it's completed one period, right? So it all depends on where we are starting from. One complete wave, how long that takes is the period. And frequency is just the number of oscillations per second, right? And we measure this in hertz, which are equivalent to 1 over seconds, right? Or seconds to the -1 exponent. So those are really closely connected, Period is equal to 1 over frequency, and frequency is equal to 1 over period. If you ever forget that, I believe it's in your data booklet, or you can just take a look at the units. As long as you're remembering hertz are 1 over seconds and period is seconds, right? We can quickly convert those between each other. All right, here's where we get into some new IB stuff not covered in Alberta. And it can be a little confusing because we're bringing in circle geometry into this whole idea of simple harmonic motion. So phase difference, that was briefly touched on in the Alberta curriculum, right? Things can be in phase or out of phase, but we never talked about it in terms of an angle, right? So this is where the connection between uniform circular motion and simple harmonic motion really kind of picks up, because often when we're talking about simple harmonic motion, we will be talking about phase difference in their angles rather than a distance between them. So as you can see here, we have the trough of one wave function or one object's simple harmonic motion and the peak of another lined up. So as they go, right, as long as they have the same period, and here they even have the same amplitude. So it's essentially the same simple harmonic motion, just shifted. So let's say this one started here, right, and then as it came up and back down, right, the second one is starting when the first one has undergone half of its period, or half of that first wave. Right? And if a full wave can be thought of almost like a circle, right? Because it's going around. So here I'll just skip forward to the next, and hopefully that helps make more sense, right? If we're starting here and traveling up, if we're just looking at the x component, right? Our x component will be getting bigger. Sorry, let's look at the y component, right? Say we're starting here, we're looking at the y component. Our y component starts at 0, right, and it's getting bigger until it reaches its max, right, and it'll come back down, back to equilibrium, right? So that's essentially what's happening for this first half of our wavelength, or half a period, for this top simple harmonic motion. And once it reaches this point, we have a second object that's going to start the same motion, but it's going to be 180 degrees or pi radians behind. Hopefully that connection becomes more clear as you go through these slides and watch some videos or ask me for some additional guidance on that. All right, so after 180 degrees of that unit circle, our second one is starting, and they're going to continue their simple harmonic motion with the same period, the same frequency, same amplitude, all the way through this cycle. But this one will always be exactly 180 degrees behind. Okay, so this one is 180 degrees behind. Another way to do it would be to be 90 degrees off, right? So that would be, again, if we're looking at our y component of this unit circle, this one will start its simple harmonic motion. It'll go for 90 degrees or pi over 2 radians, and then our second one will begin from here, right? So we end up always being 90 degrees out of phase, or pi over 2 radians out of phase. So phase difference will always be the time difference or phase angle by which the wave or oscillation leads or lags the other. So we would say this one is leading. It comes first. It leads this second red wave by 90 degrees. Right? Or you could alternatively say the red one is lagging the pink one by pi over 2 radians. Alright, so if you haven't had a chance to watch this video, I highly recommend it. So give that a go, pause this video and go to that one if you haven't already watched it. So, simple harmonic motion is always periodic motion. So it has a constant period in which the restoring force or the acceleration, is proportional and in the opposite direction to the displacement. So right off at the beginning slide of this one, we saw that our green acceleration was always proportional but opposite that of displacement. Right, so some examples would be a marble rolling back and forth almost like a pendulum in a bowl, right, where the restoring force would be gravity trying to bring it back down, and it's always going to be opposite to the displacement, right? As the displacement is going up in the positive direction, gravity will be restoring it or pushing it, accelerating it down in the negative direction. Same for a diving board, right? But we're working more with an elastic force there. So as you push down the diving board, the elastic energy stored in the diving board will create a spring force or an elastic force upwards opposite that displacement. And as it releases, right, it'll push up. This is similar to the meter stick that the last video was using. So as it goes up, it will have an acceleration or restoring force pushing it back down to the equilibrium, right? Or you could think about a car hitting a wall and bouncing back, or a car this is a car bouncing up and down. I don't know if you've seen that lately. I think that's a bit of a fad. Right, so here is our proportionality between acceleration and our displacement. They're proportional, right, but they're opposite. So as our displacement is moving to the right, our acceleration is moving to the left. As our displacement is moving to the left, our acceleration is moving to the right. And they're both zero at this equilibrium position. Right, and acceleration force is equal to mass times acceleration. We're not changing the mass, so our force and our acceleration are directly proportional. All right, Hooke's law, time to do a little more review. This was our third unit in Physics 20. Force of a spring is equal to the negative spring constant times its displacement, right? Where force is equal to mass times acceleration. So another way to think about this, the acceleration is proportional to that negative displacement. So they're always going to be opposite but directly proportional. All right, so as this spring is moving up and down, if we were to drag a piece of paper under it, right, and it was drawing this line on it, we would see that it would make this nice sinusoidal path with this displacement versus time. And our period will be the distance between any two peaks, right? We could have just as easily chose this equilibrium position, and that we're going to have the same period, and the amplitude is that maximum displacement away from our equilibrium position. And there's a cool sinusoidal function. This must have been taken way up north where the sun really never sets, and it just starts to come back up. Okay, so more recap. Maximum velocity is occurring at this point where x is equal to 0. So there's no the acceleration is 0, displacement is 0, but velocity is maximum. So this is where the phase kind of comes in. So when our displacement is 0, our velocity is maximum. So we could either say, let's just take a look at this. The peak here comes, right, 90 degrees in front of the displacement, right? You can always do a double check if you're not sure if that's 90 degrees. That's a quarter wavelength, right? So 90, 180, 270, 360, or pi over 2, pi, 3 pi over 2, 2 pi radians. Okay, so we talked about it in Physics 20 in terms of wavelengths or a quarter of a period. We're just changing that vocabulary now to include our angles, our angular displacement, right, our phase difference. So this one is a quarter wavelength in front or leading by a quarter wavelength. So we would say this is leading 90 degrees or leading pi over 2 radians. And that's always going to be true for displacement versus velocity, right? Maximum acceleration, since it's directly proportional but negative of our displacement, right? It's always going to be maximum acceleration when we have maximum displacement. It's just going to be the opposite sign. And also another important note, we're going to have zero velocity, right? We've come to rest at that point at the very top or the very bottom, right? No velocity when we have maximum displacement and maximum acceleration. So graphing now displacement against acceleration, right? They are proportional but opposite. So this one's on its way up, whereas acceleration is on its way down, right? So let's take a look at how much this is leading or lagging. So we're starting up here, that we reach our peak and we come back down, right? And this is where we kind of start our acceleration. So we've gone half a wavelength, which corresponds to 180 degrees or pi radians. So this one could be said to be leading by pi radians, right? Or, right, when we're working with exactly 180 degrees or pi radians, you could just as easily say that this one is leading by pi radians, because if we were to start with the acceleration, right, by the time we reach this point, right, that's where we're going to start there. So leading and lagging becomes less important with our displacement and acceleration whenever we're working with exactly 180 degrees or pi radians. All right, we also worked with this formula in Physics 20. Hopefully it's familiar to you. The period is equal to 2 pi times the square root of the mass of the spring, or of the object on the spring, divided by the spring constant. Right, and now you can really clearly see, hopefully, where this 2 pi comes from. This is all related to that unit circle and that complete rotation of our simple harmonic motion object undergoing simple harmonic motion. Okay, so an oscillating mass. These were also briefly touched in the Physics 20 course. We'll just quickly go over it. Kinetic energy will be maximum when we have maximum velocity, obviously. Kinetic energy is half of m, or mass, times velocity squared. So if we have maximum velocity at the equilibrium, we're going to have maximum kinetic energy, right? And potential energy is always going to be when it's at its highest point or when the spring is storing the most energy, right? Depends if we're looking at gravitational potential energy or spring energy, stored spring potential. So here's a cool graphic for you to hopefully really clearly see this relationship. So starting with kinetic energy, it's going to be maximum right in the middle of this object's motion, that equilibrium, right? And it's going to be 0 at either end. Whereas our gravitational potential energy will be 0 at the bottom, right, and maximum at the top, right? When it's at the top, it's actually only gravitational potential energy. And the energy of this potential elastic, right, the spring elastic energy, is going to be maximum when it's at the bottom, right? That's when it's going to have the largest spring force or elastic force trying to push it back up to equilibrium, right? And at the top, we're replacing that with our gravitational potential energy. So kinetic energy is maximum at our equilibrium point, x equals 0. Potential energy is maximum at either the top or the bottom of the motion, which would be our amplitude, right? Our positive x naught or a negative x naught. All right, we'll continue this tomorrow, hopefully. If not, after spring break. I'll get a lab uploaded for you that I recorded for you. So give that a go once you've figured out, right, re-gone over these notes and some videos and possibly your Physics 20 material. All right, see you guys.